Alright, 4.3 talks about the substitution method. That's extremely important. We did this already, guys. We did this when we used the chain rule. So here you're trying to undo the chain rule. Do you remember what we let u equal when we did the chain rule? The inside of a power function, the inside of a radical, the denominator of a fraction. Well, we do the same deal here. Let's start with the first problem. On numbers, this on page 346. And the first two problems, they tell you what to choose. But if you were gonna pick, wouldn't this be the inside of the radical, the power function? So this integral becomes the integral of u to the fourth. Do keep in mind, I still have those to worry about. There's a dx. So if I take a derivative of this du dx, that would be what? 4x. And if I cross multiply, thanks to Leibniz notation, I notice x dx, this part is right there. So using algebra, if I'm off by a constant, I can get away with it. X dx is simply du over 4. Du over 4. And do you see what just happened? This is now just the integral of u to the fourth with a 1/4. I could take the 1/4 up front because it's a constant and integrate u to the fourth du. And what would that be? Wouldn't that be 1 over 4? Add 1 to the power. Divide by that. And 1 over 20 times what? I can fix this problem easily. That would be 1 over 20 times u raised to the fifth. Don't forget the plus c. And what was u again? U was 2x squared plus 3. So this is what you take a derivative of to get that mess. And if I look at number 4, you notice also this is the power function. You let u equal the inside of a power function. There it is. Now this is the integral of, instead of the sign, we're going to use a u. And if I take a derivative of that, du d theta in this case is the cosine of theta. And if I cross multiply, du will be the cosine of theta d theta. Well, isn't that this? Isn't that just u cubed over 3 plus c? And what was u? Wasn't u a sine? And that's pretty much how this game is played. Really, really simple once you get the hang of it. So if I look at number 8, what am I going to let u equal? I'm going to let u equal the argument, the radicand, the denominator of a fraction, the inside of a power function, the exponent of an exponential, the argument of a log on the long run, always. So I'm going to let u equal x cubed. And since I'm going to take du dx, that's 3x squared, and I'm going to start multiplying, and I'm going to do that every time, I'll start eliminating this step and jumping from this to this straight. Let me see how this works. I'm looking at the sine of, and u is x cubed. And do we see that x squared dx is really right there? But there's a 3 standing in the way. You could be off by a constant, and I could automatically drag the 1/3 out. And wouldn't that be 1/3? What do you take a derivative of to get sine? Isn't that negative the cosine of u plus c? So my final answer is negative 1/3 the cosine u was x cubed plus c. And I could check my work really quick. If I take a derivative of that, that will be negative 1/3. Derivative of cosine is negative the sine of x cubed times 3x squared. The negatives cancel out, and the 3's cancel out. And guess what I'm left with? Pretty cool, huh? Alright, how about this problem? What am I going to let u equal? Well, it's no big secret. The inside of a radical, the denominator of a fraction, the argument of a trig function. So du, instead of writing du dt equal, I'll just say that's negative the sine of t dt. Save myself that step. This becomes the integral. This is my u, but it's underneath a radical. And sine of t dt is off by a minus. That's a small price to pay. And doesn't that become negative? Isn't that u to the 1/2? Don't you add 1 to the power, divide by that? And what was u? U was 1 plus the cosine of t. You could leave it to the power of 3/2. I really don't mind. That's the same thing. And what do you think I'm going to let u equal in this case? The argument, the angle of a trig function. I'm going to let u equal the cosine of x. Du will be negative the sine of x dx. And let me not lose track of what is what. This is the sine of u. And sine of x dx is negative. I don't know why everything shifts to the right. Negative du. Now, what do you take a derivative of to get sine? Negative the cosine of u plus c. So that turns out to be the cosine of u. And what's u? U is the cosine of x. I could check that again. If I want to take a derivative of this, the outsidemost function is a cosine. That's negative the sine of the cosine of x times the derivative of the inside, which is a negative sine of x. Those negatives cancel out, and there it is. So what do you think we're going to let u equal number 16? The argument, the radical x. What's the derivative of a radical? We said square root 1 over twice the square root of x dx. So too many square roots floating around. I suggest you start with what you chose and get that out of the way and look at what's left over, and hopefully du picks that up. It does, off by a half. That's easy fix. That is negative twice the cosine of u plus c, or simply negative twice, sorry, that was my phone, negative twice the cosine of u plus c, and u was what? The square root of x. I don't know, kind of fun. Techniques of integration are very challenging, but this is the only one you're going to learn in this class. There's one minor exception when it's a definite integral. We'll talk about that. But for now, what are you going to let u equal? I'm going to let u equal 1 plus tan of t. What's du? Isn't du the secant squared of t dt? Wouldn't that become the integral of the square root of u? Now, you do recognize that those are the same. That is the integral of u to the negative 1/2 du. Add 1 to the power, divide by that, right? That would be twice the square root of u, and u was initially 1 plus tan of t. Alright? And if I look at problem number 26, I'm glancing at this and I'm trying to figure out how this works. Well, let me think a bit now. I want that to be my du. Something that you need to do a lot of thinking of in the next course, not in this class. For now, minor thinking. If I want du, the derivative, to be secant squared, shouldn't u equal the tan of x? If I let u equal the tan squared of x, I'm in trouble. Because derivative of tan squared is twice the tan of x times secant squared of x. That's not what I have. Instead, I think about it just a bit, saying, this is what I want my du to be. What do you take a derivative of to get secant squared? Again, in this class, you don't have to do that a lot. You take a derivative of tangent, that's secant squared of x dx. But in 5b, that's something that becomes a must. So that is my u squared, and that is simply my du. So that is the integral of u to the negative 2 du. Add 1 to the power, divide by that. And that is negative 1 over u is tangent of x plus c. So this is negative cotangent of x plus c. By the way, I do want to mention, this is not the only way you could do this problem. You could have manipulated those two sines and cosines and proceeded. That does work sometimes to be quick and efficient, depending on what you're doing. I would like to look at those problems right there. So glancing at this problem, I have two options. Option 1, I could say let u equal x squared. du is 2x dx. This is the integral. This is my u. Always get that out of the way. And do you see that this is 1/2 du? So for this class, it turns out not to be a massive deal. If you just leave the limits for now, say that is the sine of u, right? And then say that is 1/2 the sine, and u was x squared, evaluated from 0 to radical pi. That would be 1/2 times, plug that in, the sine, when you square that, that's pi, minus the sine of pi, the sine of 0, which is, oh, that's both, which is 0. Something you should consider, and I suggest you do that. You're only allowed to do that if you have a definite integral. I'm integrating this problem. I do the same, let u equal x squared. du is 2x dx, and I'm still going to divide by the 2. So that part is not going to change. And I'm going to say this is the integral of cosine of u du with 1/2. But now, instead of saying this is running from x equal to x equal, I'm going to take 0 and plug that in. And that's going to make that u equal. So if I put 0 and I square it, that's 0. And if I put radical pi in there, radical pi squared turns out to be pi. I don't have to go back to x. In 5b, that saves you a lot of work. So that's going to be the sine of u evaluated from 0 to pi. You do get the same exact result, but it would be much easier for you to start doing that instead of going back to x. I was going to do 2 more, but I'm out of time. I do want to talk about a very important property, which says if you're integrating an even function from negative a to a, then you could use the mirror image and double it from 0 to a. And let me put the graphs there. There it is. If you're dealing with an even function, then you could really find this and double it, since those are the same. And if f of x is odd, you integrate, again, the key is from negative to a. The integral, isn't this going to be negative and this going to be positive, and they're going to equal to each other, and that's going to cancel out? So if I'm looking at problem number 46, if I look at this, if I throw a negative in and raise it to the 4th, isn't that x to the 4th the sine of x with a negative? Isn't that negative x to the 4th sine of x? So this is an odd function. This automatically equals 0. And that's how simple it is. If you see it's odd, it's easier to do it from 0 to a. Not that it matters. And if you know it's even, I'm sorry, but if you know it's odd for sure, then there it is, and there's the homework.